on behalf of the Center for Simulational Physics in the Department of Physics and Astronomy, I will extend you a heartfelt welcome to the fourth Chhabra-Landau lecture. So for those of you who are maybe not familiar with this lecture series, it was established to celebrate the work of our distinguished colleague, my case friend, Professor David Landau, who has had a huge impact on the field of simulational physics, in particular on Monte Carlo simulation. It's not just that scientific aspect, it's also his contribution towards teaching students over many years, a long career, by establishing the Center for Simulational Physics and sustaining it for all these many years. And so we celebrate that. It was started by, what makes it really special is that this all funding or support comes from an endowment by his own former student, Dr. Ashwin Chhabra, who's actually here on Zoom. I just saw him earlier. And that makes it quite special. So Dr. Ashwin was a student here several years ago. He did his master's degree under the direction of Professor Landau. And then he went on to get his Ph.D. at Yale, and then became the president of what is called the Euclidean capital. This is not the Euclidean geometry, but this is a different sort of Euclidean, which, by the way, manages Simons Foundation's investment. Those of you who know the Simons Foundation, one of the top, the most prestigious science supporter, foundation that supports basic research in science. So he's here with us. And so this is the fourth talk. We have had 3 lectures in the past with distinguished professors, speakers. Those of you who have attended, all of them witness to that. And today we have the fourth lecture given by Professor Stephen Louie, very distinguished professor from at the University of California at Berkeley. So with this brief introduction to the Chhabra-Landau lecture, I have now the privilege of introducing Professor Stephen Louie. And I'll just tell you very briefly his long and prestigious career. He did his PhD at the University of California at Berkeley in 1976. And then afterwards, he had a lot of very high-level jobs, including IBM Watson Research Center, and then followed by Penn Laboratories, researcher there. Then he joined the faculty at the University of Pennsylvania, and then he joined UC Berkeley faculty in 1980. He's identified as by ISI as one of the most highly cited researchers in physics. Those of you who understand the H-index, his H-index is 168. That's a big number. Just to give you a perspective, Einstein's H-index is 123. So obviously, Steve is way bigger than that. He has over 650 papers. That's a lot of papers. And of these, 22 of them have citations over 1,000 times. And a number of them out of these have been cited 3,000 times. So he is most known. He has a lot of firsts. You look at his Google Scholar, you see a lot of new beginning work by his group. But he's also most known for GW ab initio method. Don't ask me to define it yet. Hope you can talk about it a little bit. He has a lot of awards and recognitions. He is the member of the National Academy of Sciences. He's a fellow of the American Physical Society. He's also a senior faculty scientist in theory, facility director of the Molecular Foundry at Lawrence Berkeley National Laboratory. He's editor of the journal Solid State Communications. He was awarded the Sloan Fellowship, the Guggenheim Fellowship, and 2 times Miller Professorship. And he's a U.S. Department of Energy Award has received the DOE Award for Sustained Outstanding Research in Solid State Physics, as well as the Lawrence Berkeley National Laboratory Outstanding Performance Award, and the UC Rahman Prize for Computational Physics of the American Physical Society, the Davisson-Germer Prize in Surface Physics of the American Physical Society, and last but not least, he has shared with Marvin Cohen the Foresight Institute Richard Feynman Prize in Nanotechnology. So, the list goes on. And so we're so excited to have him here. And as a small token of appreciation, we have some thing to give you, Steve. This is for you.
Oh, thank you.
Thank you for coming, and we're very excited you're here.
Thank you.
So that's yours.
Okay. Well, first of all, I would like to thank Professor Abate for such a kind introduction. I'm extremely honored and pleased to give today's lecture. I understand that Dr. Chhabra has endowed this lecture series, so we had to thank him, and he's is an alumnus of this department and a great benefactor as far as I understand. So I'm very happy to have a chance to say hello to him just now. And of course, I know Professor Landau for over 4 decades, I think. And our paths have crossed many times over the years, and we serve on subcommittees together. So what I want to do today is in this lecture is to give you some idea, some of the things that I've been working on in my group, looking at the property of 1- and 2-dimensional materials. As you all know, materials play such an important role in shaping human history that we use them to name the periods of history, starting from the Stone Age all the way to the Industrial Revolution and to the present time. Now people talk about perhaps we are in the Silicon Age, the Plastic Age, or the nanomaterial age. And what we mean by nanomaterial is that materials that has dimensions that is at the in the nanometer scale, at least in one of the directions. So the focus of the talk is then today is to look at nanomaterials. What do we mean by nanomaterials? As I mentioned, these are materials with structure that at least along one direction is in the nanometer scale. So we have a 0-dimensional material, which include atomic clusters, nanoparticles, quantum dots, or 1-dimensional material that includes nanotubes, nanowires, nanoribbons, and then 2D materials, which consists of semiconductor quantum wells, graphene, atomically thin crystals. So in today's lecture, we're going to focus mostly on 2D materials. So this is a really active and rapidly developing field, which has generated a lot of new science and promises for application. The most well-known example of a atomically thin 2D material is graphene. Graphite is a layer material with sheets of carbon atoms interacting very weakly with each other. So if you were to isolate one sheet of this carbon atoms, then you have graphene. And it turns out that the low energy electronic states of graphene has a dispersion relation which is linear. And so they behave like 2D massless direct fermions. And this is the reason for many of the exciting property, electronic property of graphene. In fact, Geim and Novoselov received a Nobel Prize in 2010 for their work in this area. In nature, there are many, many more layer materials, and many of them can now form into two-dimensional crystals. Some of them are semiconductors and metals. Others are insulators, superconductors, and magnets. And even more interesting.
Can you go closer? The Zoom people are not listening to you.
Oh, yeah, so I had to stay here.
Thank you.
All right. I'm not sure I could see myself. Even more interesting is that you could stack them together and form new materials with emergent properties. Looking at solving for the property of materials is basically an n-particle quantum problem with electrons and ions interacting with each other via the Coulomb interaction. However, the number n here is very large, in the order of 10 to the 22 per centimeter cube for a macroscopic sample. So that's impossible to solve exactly from first principles, which, however, is also the reason for the richness of the field of condensed matter physics and material science. So let me pause here to pay tribute to our Professor Landau here. In fact, he is one of the pioneer and giant in developing and applying many-body methods to realistic physical systems, especially on phase transitions through models and computation and simulation. So I'm really happy that I'm able to give this lecture today. As I mentioned, it's not possible to really solve this problem completely from first principles. However, it is in fact often not even desirable to get the full solution because the full solution will be so complicated. It's better actually to focus on some physical quantity that is closely related to the properties that you're interested in, and then make approximation to those physical quantities. So I'm going to tell you about one particular approach of attacking this problem. So for example, if you're interested in single particle-like behaviors in a material, for example, in understanding a tunneling experiment, then it's better to, instead of looking at the full solution of your many-body problem, to look at the probability of finding a particle at position r and time tau, given that you create one at r prime and time t equal to 0. Now, this, in fact, is the interacting Green's function. And if you know this Green function, then you could obtain the single particle-like excitations in an otherwise interacting many-body system. And this is what we call an n+1 particle problem. If you're interested in the optical property of materials, then you have to look at the two particle interacting Green's function and in this what we call the n+2 particle problem, because when a photon is absorbed, you're creating an electron and a hole in your material. So, for example, if you look at the quasi-particle excitation in a solid, then the excitation energy, in fact, is modified due to the many-body interaction via a term, what we call self-energy. And this energy is related to the poles of the Green's function in energy space. And the self-energy, sigma here, this term, can be obtained from many-body perturbation theory. That is, expanding it in terms of Feynman diagrams of increasing orders. It turns out that it's much more efficient to do this expansion in terms of a screen Coulomb interaction as opposed to the bare Coulomb interaction as you've seen in standard textbooks. The reason for that is because the screen interaction in general will be much weaker than the bare interaction. For example, in the case of silicon, the screen interaction would be an order of magnitude smaller than that of the bare interaction. It turns out that for many materials, not all materials, it's sufficient to take the first turn, where here this double dash line is the screen Coulomb interaction. And this is what we call the GW approximation, where G stands for the Green's function and W is the screen Coulomb interaction. And you could do the same trick for the two-particle Green's function and obtain the optical properties, including electron-hole interaction effects, excitonic effects, via the beta-salpeter equation, and that's called the GW beta-salpeter equation approach. To illustrate how well this kind of approach can obtain realistic results that matches with experiment, let me give you two examples here. These are calculations that done without any adjustable parameters. On the left here is a comparison of the calculated band gap with the experimental band gap for a series of insulating materials. And you see that the GW method actually gives you very, very accurate answers, whereas the band gaps from density functional theory, for example, will give you gaps that significantly off from experiment. And on the right is a plot of the optical absorption spectrum of silicon. And you see that by solving the two-particle Green's function, you could actually get the absorption spectrum agrees very, very well compared with experiment. This slide shows you the kind of progress that we have achieved, we mean the whole community, in the last decades for this kind of ab initio calculations. This shows the number of electrons that can be attacked as a function of year. In the 80s and the 90s, we could basically look at system with a few atoms per unit cell. However, with increased capacity of computers and development of improved algorithms, we could now look at systems with tens of thousands of atoms in the unit cell. And in this talk, I will focus mostly on the electronic and optical property of quasi-1D and 2D materials. Because of their restricted geometries, their behavior actually are strongly influenced by quantum confinement, enhanced many electron interaction, and symmetry and topological effects. And this kind of effects can give rise to novel properties and phenomena that do not exist in the bulk case. And they can be quite useful in applications, for example, photoelectronics, energy conversion and generation, and so on. What's even more remarkable, as you will see, that these properties can be tuned by gating and environmental screening effects. So this is going to be the outline of the rest of the talk. I will first discuss the electronic topological phases in graphene nanoribbons, and then we're going to talk about the interaction and time-dependent phenomena in photophysics of atomically thin 2D crystals. And then finally, I'm going to show you some very recent work we had done on novel Moiré excitons in twisted bilayer transition metal dichalcogenide heterostructures. So let me begin by reminding some of you some basic solid-state physics. Because of crystalline periodicity, we have Bloch's theorem, which says that the electronic states in a crystal are propagating states. They can be characterized by two quantum numbers, a band index and a k vector. And the wave function in general can be written as a phase factor times a function that's completely periodic from one unit cell to another unit cell. So you have a kind of a band structure, and this band structure can have band gaps. If the Fermi level is in the band gap, then you have insulating materials. Otherwise, you have metallic systems. The distinct bulk states exist only in a finite region of K-space, and that's called a Brillouin zone. The Brillouin zone, in fact, is a compact geometric manifold, and this will be an important concept when we talk about the topological phases of materials. So in one dimension, the Brillouin zone is just a circle, and in two dimension is a donut, 2D torus. So now let me turn to graphene nanoribbons. They are just basically a strip of graphene with a diameter, with a width in the order of a few nanometers. Of course, you could cut graphene into different ribbons with different shapes and width. So this is what we call a zigzag nanoribbon, because the edge looks like zigzag-like. And this is what we call armchair graphene nanoribbons with an armchair edge. It turns out that this semiconductor graphene nanoribbons are all semiconductors if you don't do anything to them, and they have very novel electronic and magnetic properties. When we first worked on this kind of system more than 17 years ago, this was kind of toy models for theorists. However, there have been a tremendous renewed interest in this area because of the discovery of an experimental way of making graphene nanoribbons using a bottom-up synthesis technique with precursor molecules. So to look at the topology of the electronic states of this kind of system, let me remind you also what we mean by looking at the topology of something. Topology is a study of global property of an object preserved under continuous deformation and characterized by some kind of invariance. On the other hand, geometric properties, such curvatures, are local properties, but integrals over local geometric properties may characterize the global topology of a system. So a famous example is the Gauss-Bonnet theorem for a 2D manifold. You take the integral of the Gaussian curvature over the surface, then it's always equal to 4 pi times 1 minus a number called a genus. So both a cup and a ball has a genus of 0, but a ball is not equal to a donut because a donut has a genus of 1. So you could deform a cup into a ball, but not a ball into a donut. The topology of electronic states in the Brillouin zone for the role of the geometric local geometry is in fact taken by a quantity we call the Beery connection, which is basically given by the inner product of the periodic part of the plot function with the gradient of that function. So the study of non-trivial topology of black bands has led to a much deeper physical understanding of many phenomena, including protective boundary states, integer quantum Hall effect, and discovery of new phases of matter. In fact, the Nobel Prize in 2016 is given to these three gentlemen for their work in this area. And in one dimension, you can have symmetry-protected topological phases, which are basically dictated by a quantized Beery phase, an electron pickup across the Brillouin zone for the electrons in occupied states. And this is characterized by an invariant. We call that Z2, which is either equal to 0 or 1. And Z2 is defined through this relation connected to the Beery connection that I defined for you in the last slide. So for graphene nanoribbons and many 1D materials, you could think of them as having Z2 equals 0. That is, it's kind of like a regular strip. But when Z2 equals 1, then the wave function, the electronic structure is non-trivial. And you could think of it in terms of a Mobius strip that is the wave function as it goes around the Brillouin zone, in fact, has a twist to it. So what we have discovered in the last few years is that the graphene nanoribbons, called GNR, with time reversal and spatial symmetry are really large gap semiconductor that holds this kind of symmetry-protected topological phases. And because of the boundary, bulk boundary correspondence, there will be topologically protected boundary states between segments of different topologies. What's more interesting is that Z2 can change with the different termination of the unit cell, then that really adds richness to the physics of this kind of system. And in fact, GNR systems with no spatial symmetry and approximate chiral symmetry may be used with a Z classification. I won't have time to talk about this. So let's focus on some examples. For example, if I look at a finite segment of n equal to 7 armchair graphene nanoribbon, picture that here, if the ribbon is terminated like this, which has a zigzag edge, then if you calculate what Z2 for this material is, it's equal to 1. And of course, vacuum is a trivial insulator, so Z2 is equal to 0. So this two segment then has a different topology, and that would guarantee you actually have a end state, interface state right here. So that corresponds to having a new state in the middle of the gap for such a semiconductor. And in fact, this kind of end state has been seen in experiment early on. And this is some STM picture of such an end state, except that it's never interpreted in terms of this kind of topological concepts. What's even more interesting is that if you form a junction between two graphene nanoribbons, for example, forming a junction between a 9 AGNR and a 7 AGNR like this, when you have two ribbons and join them together, because you have structure of the ribbon, you could join them in a different way. here I show you one way of doing it to make the bottom edge straight, so that this junction is somewhat asymmetric. And you can calculate what Z2 on the left is and Z2 on the right is. They turn out to both equal to 1. That means that those two segments are topologically equivalent, so there's no interface state there. On the other hand, if you shift the right ribbon a little bit, my right, and then join them together, you form a more symmetric junction. And in this case, Z2 on the right becomes 0. So that means that these two are now topologically equivalent, and there will be one interface state right at the junction. In fact, if you do a full calculation, you will find there indeed is an interface state, and this is the wave function of the interface state. And the reason for this change is that when you go from the top to the bottom here, you are forced the unit cell on the right-hand side to change from something looking like this and something looking like that, and that results in a different Z2 invariance for the right segment. And this kind of results motivated us and lead us to what we call a topological engineering, that is using this kind of topological state to change the band structure of your material. So for example, if I take this 7-9 junction and flip it around and join them together to form a superlattice, then you would have a lattice with two topologically protected states in the gap, and they will interact with each other. And those topological states, in fact, will form two bands within the bulk band gap, and whose property can be changed by just changing the length of the segment. Motivated by this discovery, my colleagues, Mike Homey and Felix Fischer at Berkeley were able to actually make this kind of superlattice. So this is the sample they make. This is the STM image of the material, and you could clearly see there are n equal to 9 and n equal to 7 segments. And they could probe the electronic state of this superlattice using STM measurement, scanning tunneling microscopy spectroscopy. So according to our theory, given here on the right, there are two topologically induced bands in the band gap, and the wave function of those states are plotted over here. And when Mike Homey and Felix Fischer did their measurement, they could measure the density state, and they indeed see two extra peaks in the density state, and those peaks give rise to DID maps, which maps out the wave function of the state, and they have exactly the characters that is predicted by the calculation.
So what determines the bandwidth of the topological bands?
That determined by the interaction between the junction states. Yeah, the junction state decays into the bulk, and the length of the segments will determine the hopping from one side to one junction state to another junction state.
And
so
the energy, is there something that guarantees the energy is at a certain place?
The energy is guaranteed to be in the gap because these are topological states.
Right, but you could have an interface or disordered state too, right?
Excuse me, I did not hear you.
I could have a defect state there too.
Yes. Those are additional states which can be eliminated but the topologically protected states cannot be eliminated. Even more, so you can change the band gap between these two topological states and the bandwidth for those states by just changing the segment length. One would expect to have a magnetic ground state if the on-site Coulomb interaction is bigger than that of the hopping, the gap or the hopping energy between the junction states. And in fact, you could form stable spin centers, therefore, novel quantum spin chains by setting the hopping integral to be small compared to on-site U, which you could do by varying the segment length. And even more interesting is that this superlattice itself is a crystal. So if you look at the N of such a superlattice, it ought to have N states if it's a topologically non-trivial material. So in fact, if you look at this system and have an N look like this is what experimentally has been found, then what you find is that you should, according to the theory, there are topological N states over here. And one could now then compare with experiment and look at those N states. So I'm going to focus on looking at this particular N state between the two topological bands and the character or the state of those bands. So what you find is what's on the right-hand side. For the topological bands, they are extended states. Then for this N state in the gap, in fact, it is a localized state. It's localized on the end of this superlattice. However, it's unlike a defect state from a dangling bond at the surface. It actually is completely extended in one supercell and then zero otherwise, exponentially decayed. So this really indicates that it's come from topology and not from some kind of chemical defect. So motivated by this kind of theoretical development, in the past few years, we, together with experimental groups at Berkeley, Mike Cromie, Felix Fischer, and Fang Wong, we have been looking at a number of different systems involving this kind of junctions, and we have been having a lot of fun doing that. Now, let me turn to the second topic I want to discuss.
Can I ask you?
Sure.
So it's very fascinating. You have a general, bigger picture of manipulating these connections.
Yes.
But is it really that different from sort of like a moire? All you're doing is
From what?
from moire type of thing. The moire.
No, it's not, because this origin from topology.
But ultimately, you are overlapping, the bands and so on, right?
Right. So
It's just it's a bigger picture. There is a topology governing the motion.
yeah, well, the topology gives you the states that you can manipulate and interact to give you the new bands. That's why we call that topological band engineering. So you need the concept and understanding of topology to do that first. I'm going to talk about Murray physics later. Okay, so as a second topic, I think I'm running very late due to the technical difficulty. I hope you would have the patience to understand that I'm probably going to run over time. So we're going to look at interaction and time-dependent phenomena in the photophysics of atomically thin 2D crystals. There are a number of newer phenomena that occurs in this kind of material that does not occur in real materials, in bulk materials. For example, correlated multi-particle excitation with very large binding energy, and giant exciton enhance the shift currents, the so-called photovoltaics without PN junctions. And then I could also talk about a way one could now directly probe excitons and their wave function in optical field-driven pump probe angle result photoemission spectroscopy. So we're going to focus on the class of material called transition metal dicarbogenized. And you could make monolayers and few layers of this kind of material. Here is a picture of a monolayer of moly disulfide. This kind of system tends to be semiconductors, and the low energy electronic states of the system are concentrated around the K and the K prime point in the Brillouin zone. This kind of system have very strong light matter interaction, so it exhibits novel excitonic physics, and because of strong spin orbit coupling, the spin and angular momentum character of one Wally is different from another Wally. They in fact related by time reversal symmetry, and that lead to a Wally photodichorism. You could selectively excite excitation of one Wally with certain polarization of light and not the other Wally. And that's what got people excited about this kind of 2D material and lead to the idea of Wally-tronics. That is, you could manipulate the charge, spin, and the Wally degree of freedom of the carrier in the system separately. But before I'm going to tell you about the photophysics of this kind of material, let me say a few words about electron-electron and electron-hole interaction in quasi-2D systems. One thing you know probably well is that you have enhanced Coulomb interaction in this kind of system because of the reduced dimensionality. A lesser known fact is that you can have strange and strongly spatial dependent screening in this system. This is illustrated by this cartoon. Suppose you have two charges in a 2D material. They will interact through the field lines, and the field lines can go outside of the sample. So you see that when two particles are close to each other, the field lines are well screened, but when they far away, then it go into the vacuum, the field lines, and the interaction is not screened. So you look at the effective interaction as a function of distance between two particles, then it will have a structure look like that. It's equal to one unscreened at a small distance and also unscreened at large distance. This is very different from a 3D material like silicon, where after a certain distance you have constant screening. And also from this cartoon, you could see that substrate can have a very important effect because near a substrate, the field line could penetrate into the substrate and therefore give you screening effects. So let me show you some optical spectrum of monolayer moly disulfide comparing theory with experiment. On the left here is the absorbance of the system calculated either without including electron-hole interaction or with electron-hole interaction. And you see that two curves are dramatically different, and that's due to the fact of the formation of electron-hole pairs, so-called excitons. And what happened is that in this system, which has a band structure look like that, you have optical transition between bands at different places in the Brillouin zones and between different bands. And each kind of this transition can lead to states that are bound excitons. And those bound excitons show up as peaks in the absorption spectrum. And the exciton binding energy of this kind of 2D system is really large, in the order of fraction of electron volt. This is a couple order of magnitude bigger than box semiconductor with its equivalent band gaps. And the reason for that is, as I mentioned, screening is reduced and Coulomb interaction is enhanced. So how does it compare to experiment? This is the experimental absorbance. And you see that you could clearly see the excitonic peaks and then a very strong absorption background corresponding to those excited excitonic states. And because of interaction of the formation of excitons, all the oscillator strains are moved from high frequency to low frequency, and the system becomes very efficient in absorbing light. And in this calculation, we have neglected interaction with phonons. If you include interaction with phonons, then you get this curve, which compares even better with experiment. So this is our calculation without any explicit empirical parameter, any kind of adjustable parameter. And the absorbance for half a nanometer of material at this kind of frequency for monolayer moly disulfide is around 20%, and it's very large because of excitonic effects. And for bilayer graphene, it's around 5%. For silicon, which is a solar cell material, is only about 0.02%. So that shows you the importance of excitonic effects in the photophysics of two-dimensional materials. You could also look at the details of the excitation spectrum of the excitons. On the left here is the calculated results for the series of excitons corresponding to this A transition. If you were to do a kind of textbook hydrogenic model for the excitons in 2D and adjust the dielectric screening to get you the same 1s level, then you would find a spectrum look like that, which is completely different from that of the initial result. And here, in fact, you find a very strange result that the high angular momentum state actually has lower energy than the low angular momentum state. And the binding energy for all the high energy states are now strongly increased compared to the hydrogenic model that you learned from textbook. And this is because of this very interesting and strange dielectric screening as a function of distance. For the higher excited states, the wave functions are larger, just like the hydrogen atom, and they will be sampling this part of the dielectric screening, so it's reduced. So in fact, the higher energy state has stronger electron-hole interaction than the lower energy states, and that's why all these states are now pulled down in energy. And because the high angular momentum states have a bigger spatial wave function, it sees a more attractive potential, and therefore 2p is lower in energy than 2s. Now let me say a few words about substrate screening. That's turned out to be also very important. Here is a picture of what happened when you have a monolayer of molybdenum on top of graphite. And if you put a point charge in this material, you could ask what is the induced screening charge due to the fact that you have a substrate. And that's given by this color plot right here. It's quite complicated, but it's very important in screening this charge. And in general, screening is non-local and frequency dependent. And one has to incorporate this kind of effect into the understanding the property of a 2D material in the presence of a substrate or environmental screening. In fact, we and others have found that this kind of effect is very important. For some systems, substrate and encapsulation can renormalize the band gap of 2D semiconductor by more than 50%. It can change the exciton binding energy by a factor of 2 or more. And it can also tune the energy and dispersion of the plasmons in this system, which is important for plasmonic applications. So it's very important then when somebody tells you, I make a 2D system and measure this property, one really have to ask the additional question, what environment this 2D material is in. Now, there are actually many other interesting new phenomena in 2 dimension and 1 dimension. To understand those phenomena, one has to go beyond the standard GW and GW beta salpeter equation formulation. For example, you would like to understand, correlate a higher number of particle excitations, such as bi-exciton, a bound state of 2 exciton, trions, and so on. Then now we have to look at the interacting 3 and 4 particle Green's functions. And if you were interested in time-dependent and high-field phenomena, such as those probe and pump probe experiments, nonlinear optics, and so on, then one had to look at the explicit time propagation of the Green's function. For example, the time-dependent GW Green's function in the non-equilibrium Green's function formalism. So here I'm going to give you one example of such correlated multi-particle excitations. Since correlation is enhanced in reduced dimension, it's not surprising that you're going to find this kind of multi-particle excitations in such system. Here I'm going to give you the example of bi-excitons on monolayer tungsten disulfide. Plotted here is the photoluminescent spectrum measure. And what you find is there's a peak labeled XX here, which is increase in intensity as you increase the intensity of the excitation light. And this peak has been identified as a bi-exciton, and it has been well studied experimentally. And what we'd like to understand is what is the nature of this peak. And this kind of phenomena, in fact, is important in other areas of fundamental and practical interest. For example, in exciton condensates, and in understanding how a single exciton can be split into 2 excitons, for example, in organic crystals or for photovoltaic applications. So as I already mentioned to you, within this kind of Green's functional approach, if you're interested in quasi-particle excitations, then you have to solve a single Feynman diagram. You're interested in optical excitation, including electron-hole interactions, then you have to solve 2 Feynman diagrams looking like that. For bi-excitons, which is a 4-particle excitation, then it turns out that you have to consider 36 diagrams looking something like this, which involves 4 particle lines. And it is, in fact, doable. We recently have developed the method and a computer code for such calculation. So let me show you one result, which is the case of trions and bi-excitons in monolayer tungsten disulfide. And here is a comparison of the binding energy of the trion and the bi-exciton compared to experiment. So you see that's quite good agreement, and there's no adjustable parameter in the calculation. It's really just it's the first fully ab initio many-body calculation of such material. It shows that it has a very rich energy and spin valley structure. It's a high temperature phenomena because the binding energy is very large. The theory elucidated experimental observations, but also it gives you some new predictions, in fact. So for example, this measure by exciton has been traditionally interpreted as a bound state of a bright intra-Wally exciton with a dark intra-Wally exciton. However, according to our calculation, that's not true. This biexciton, in fact, is a combination of a bright intra-Wally exciton and a dark inter-Wally exciton. And this kind of configuration was not considered before because of the neglect of the many-body electron-hole exchange effects. Now let me spend a few minutes to talk about field-driven time-dependent phenomena. I won't go into the details of the method since I'm running out of time. Let me just show you that you can apply this approach, solving the Green's function in real time, and then look at various quantities you could get out from it. One such quantity is the shift current, which is a photo-induced DC current in non-central symmetric crystal without having PN junction, the so-called bulk photovoltaic effect. It's a second-order optical response. That is, an incoming optical field could generate a DC field for a homogeneous sample. And that's related to the band topology of the material. And here is some results for monolayer germanium sulfide. And calculated here is this shift current coefficient. The blue curve is without electron-hole interaction included in the calculation. The red curve is with electron-hole interaction. So you see that with the inclusion of excitonic effects, you could have an enhancement by a 2-order magnitude in the DC shift current generation. So this is quite interesting because excitonic effects are very important in 1 and 2D, and therefore one could hope to use this kind of effect for photovoltaic application in this kind of materials. Another application of this kind of time-dependent method is to look at excitons using time-resolved photoemission experiment. That is, you pump the system with optical field and then you do photoemission later to probe the sample. So here is one such simulation. This is for monolayer germanium sulfide. We pump the system with a light that has frequency close to the excitonic excitation energy of the system, and then do photoemission probe at some delay time. On the left here, in this figure, is such photoemission spectrum. What you see without electron-hole interaction included in the simulation. And what you see is what you expect. These are the occupied valence bands, and you could see some of the states in the conduction band due to the pump light. On the other hand, if you include electron-hole interaction and do the full Green's function calculation, then you see additional features in the gap. And those features, in fact, are related to the excitons in the system excited by the pump light. We saw that by looking at the position of these new features and the width in K-space of those new features, you actually could directly get out the excitation energy and the wave function of the excitons in the system. So this is a new way of probing the excitation of the system by doing pump probe angle result photoemission experiment. And this kind of experiment nowadays are doable using laboratory setups. If I could take another few minutes, I could tell you a bit about moirate excitons in twisted bilayer transition metal dichalcogenide heterostructures. As you probably already learned from various seminars and talks, that this is a quite exciting area in modern condensed matter physics now. There are many exciting new phenomena observed in this kind of system. For example, flat bands, unconventional superconductivity, correlated insulated states, and novel Moiré excitons in such bilayer systems. I will focus on Moiré excitons for the rest of the talk. In particular, we're going to look at intra-layer Moiré excitons in tungsten diselenide, tungsten disulfide bilayers. These two layers forms a type 2 band alignment system. And if you look at the absorption spectrum or the reflection contrast spectrum, these are the results measured by Fan Wong's group at Berkeley. What one sees is that in the region where there are excitons from the tungsten diselenide bilayer, what one finds is at large twist angles, there's a single peak correspond to the so-called A exciton in tungsten diselenide. But if you make the twist angle smaller and smaller, and near zero twist angles, then this peak splits into three different peaks, three prominent peaks. So the question is, what is the origin of this splitting and what is the nature of the excitons? And simulation and calculation can help you. So an early theoretical understanding of this phenomena is through what we call a continuum model, which assumes that the excitons in this system sees additional potential due to the Moiré structure. And this can be modeled as a spatial variation in the intralayer band gap as a function of changing bilayer stacking in terms of the center mass coordinate of the exciton. An illustration of such a Moiré potential is given here. However, this model has two important assumptions. One, it neglects structural reconstruction of Moiré superlattice. And secondly, it assumes that the internal structure of the exciton is identical to that of the pristine monolayer. It turns out that both assumptions may not be valid under many conditions. For example, if you look at this tungsten diselenide and tungsten disulfide system near zero twist angle, then because of the lattice constant mismatch between the two layers, it forms a Moiré superlattice that contains nearly 40 atoms in a supercell, and there's a strong strain on the position of the atoms that lead to a very large reconstruction in the structure. In fact, the strains are in the order of a few percent, and this effect leads to flat and gap Moiré subbands with different characters, that is, different locations for the carriers or the quasi-particles in those subbands. And we did carry out ab initio GW beta salpeter equation calculation for the optical property of such a reconstructed superlattice. And what we find is that for the intra-layer absorption, what we find is that a absorbance now looks something like this. In fact, it's in quite good agreement with experiment. There are three different peaks now, and there's no adjustable in this kind of calculation, adjustable parameters in this kind of calculation. And from the solution, of the beta-salpeter equation, one could get out the exciton wave function. And then we could analyze the nature of the exciton by fixing the whole position and look at the distribution of the electrons near a hole. So on the left panel here, we saw such a movie as a function of the position of the hole. So you see that for peak 1, the exciton you find is in fact a case of a modulated one-way exciton. That is, the electron and the hole are located right on top of each other, which is very similar to the intrinsic exciton in a single layer. On the other hand, for peak 3, what one finds is that the exciton now has very different character. It has a novel charge transfer exciton character. That is, the electron and the holes are located in a separate part of real space, and the radius of the exciton, in fact, is very large, in the order of 5 nanometer. So compared to the continuum model, which gives you a spectrum look like that, and excitons always of the form of one-way excitons, the ab initio calculation gives you a new type of exciton that looks something like that. And this kind of exciton should really give you a different type of experimental signature. For example, change will occur in the absorption spectrum due to doping of electron or hole to specific stacking sites. And this kind of change, in fact, had been observed by Feng Wang's group, and that's published and shown in this publication. And exciton 3 also has should have a very enhanced diamagnetic shift due to the fact that it has such a large excitonic radius. And this kind of charge transfer exciton, in fact, according to our calculations and theory, is a very general phenomena in Moiré systems. It's due to the fact, due to the competition between the attractive potential energy of the electron-hole interaction and the interband transition kinetic energy of the flat bands with the modulated carrier density. So we encourage our experimental colleagues, in fact, to try to look for such charge transfer excitons. It turns out that the lowest energy exciton in a 58-degree twisted homobilayer tungsten disulfide is one of such charge transfer excitons. So Feng Wang and Mike Comey set up this photocurrent experiment so that one could measure the generated exciton by shining light on to the sample and then do a simultaneously STM measurement. So if you have hole, the tunneling will be different when you have electrons, and therefore give you a different photocurrent sign. And doing such an experiment, they find out that they map out the electron hole distribution for the created exciton, and that's given on the left-hand side. It clearly shows a charge transfer exciton character, and it agrees very, very well with our theoretical calculation. So let me, since I think this is your way of telling me to stop. The battery probably is dead. Anyway, so this is going to be one of my last slides. I just want to give you a take-home message saying that atomically thin 1D and 2D crystals are different and potentially very useful, basically because there is very strong many electron interaction and topological effect in this kind of reduced dimensional systems that actually lives in 3 dimensions. That's very, very important. At the very last slide, let me acknowledge my collaborator, the many excellent graduate students who have done the work that I showed you today. And in fact, many of them move on to important academic positions in other universities already. And also my senior collaborators listed here. And the work is supported by the Department of Energy, National Science Foundation, and the Office of Naval Research. Okay, thank you very much for your attention. And I'd be happy to answer any question. I'm sorry for the technical problems and for running over time.
Any questions? Yes.
Thank you for a very nice slide. So I was wondering, in the calculation of the excitonic states using the GW approximation, how much the functional from the DSE calculation is important?
For the system we look at, it's not very sensitive. As long as your GW calculations give you a good band structure to start with, then the BSE part is very insensitive to that. But for some systems, especially correlated systems, the GW band structure may depend on your starting point since it's a perturbation theory. And one has to be careful whether to use the standard kind of functional or LDA plus U and so on.
Yeah, before the next question, there is a reception at the third floor by CSP, so guys, everyone's welcome to go there. Yes.
I have a question about the like topology part you're talking about
Yes.
at the beginning about that Z2 parameter.
Yes.
I know it was like specific for those graphene like nanoversions, but is it limited to always being either 0 or 1, and like would say some other different type of nanoversion have a different, like how is that Z2 calculated?
Okay, so for systems that has time reversal and spatial symmetries, then you could use this Z2 classification, which is related to the Berry's phase that pick up by the electron as you go around the Brillouin zone. And that phase could be either pi or 0 that lead to the results of either 0 or 1. On the other hand, if you don't have those spatial symmetry, or time reversal symmetry and time reversal symmetry, then you have to do the topological classification differently. And that actually can be done for graphene system or for any system which has chiral symmetry, if you know what that is. Then it turns out that you could, the appropriate invariant is a Z invariant. That means the invariance is an integer, either negative, 0, or positive. And that gives you appropriate information about the number of protected states and, in fact, the character of the protected state.
So have you guys looked at things with like the negative integer values and just the 0 and 1 the most interesting?
Actually, we have looked at them, and for systems that breaks spatial symmetry or have magnetic properties in it, magnetism, then you cannot use the Z2 classification. And in fact, there are many experimentally constructed systems that do not have those symmetries. And we developed a Z classification and able to understand those experiments. I just don't have time to discuss it here. I could give you the reference for that paper. You're welcome.
Questions?
Any questions on Zoom?
I checked, but it seems quiet there. Not so sure why. But I have a question for you. Just while waiting. So in these Moiré structures,
Yes.
it seems somehow it's magic, right? You just rotate and that's. Is there, you think, a deeper topology in sort of why we see some exotic behavior? Do you think there is a general theory in a way that one can think of topology or anything like that?
Well, there are two considerations in this kind of Moiré physics. One is the fact that you have different stackings when you twist one layer to another layer. So that lead to structural reconstruction, and that automatically gives you a different electronic structure. And for certain twist angle, you're going to get big lattice constants for the Moiré lattice. So you end up with a reduction in the bandwidth. And so the potential energy becomes more dominant than the kinetic energy. So that leads to a lot of new physics. On the other hand, those new bands comes out may have a different band topology, and that lead to another set of phenomena. But the basic driving force is the Moiré structural reconstruction.
Okay. Any more questions? If not, probably go up to the reception, and let's give a big round of applause to Steve.
Okay.